Hi, now we've been doing a lot of conceptual work with graphs. So how do graphs connect to motion? How do the graphs connect to each other? Now we're moving into the math. So we're moving into how to solve physics problems numerically with equations. And whenever we solve a problem in physics, we're going to use a problem-solving strategy that's going to help you figure out how to solve it, and it's going to help me figure out when I'm grading if you know what you're talking about. So this is a good strategy to follow. So the process I want us all to do when we're solving a physics problem is to start, your first step is always going to be draw a picture. It helps you figure out what is going on. It helps me to say that, oh yeah, you're interpreting the question the same way I intended you to interpret it. And then we're going to determine our knowns and unknowns. So what do we know and what are we looking for? So what's our target? We're going to choose an object of interest, which, it's going to be more important once we get into forces. We got to choose our coordinate system and an origin. And we're going to put those on a picture. Then after that, we're going to pick an equation. We're going to kind of plan how we solve it. Pick an equation that's got what we're looking for. See if we have everything we need. We might need to pick another equation if we don't. So pick a second equation. Solve the equations. And hopefully we've solved the problem that way. Solve your equations. And then the very last step is one of the most important. Check your answer. Let's make sure that it makes sense in terms of the units, in terms of reasonableness. Did it answer the question? So let's practice this. I have a model rocket that is fired straight up, and it leaves the ground with an acceleration of 1.5 meters per second squared. We want to A, find out where the rocket is at 1 second, 2 seconds, 3 seconds after it leaves the ground, and B, we want to find out how fast the rocket's going at 3 seconds. All right, so first step, draw a picture. Ground, rocket. Okay, and it's going to go up. All right, my pictures are not very good. You'll probably be able to do much better than me. I'm not a good drawer. Determine your knowns and unknowns. To do this in kinematics, we're going to use a little chart, and there are 6 variables that we deal with. And so I'm going to have a chart with these 6 variables, and I'm going to do this for every single kinematics problem, because this is how I know what I've got to work with. All right, determine knowns and unknowns. Choose your coordinate system and the origin. I'll do that real quick. So I'm going to use my standard coordinate system where up is positive, and I'm going to say the ground is my origin. Okay, so put those on your picture so I know what you picked. Pick an equation, pick the second. Okay, so let's figure out what we know. A model rocket is fired straight up, leaves the ground with an acceleration of 1.5 meters per second squared. All right, and now is that positive or negative? Well, if it's going up and getting faster, it is accelerating in the upwards direction. So that is a positive acceleration. We want to find out where the rocket is at 1 second, 2 seconds, 3 seconds. Okay, so I know the time, 1 second, and then we're going to do 2 seconds, and then we're going to do 3. Do I know anything else? My chart looks kind of lonely. Okay, do I know where it started? Yes. I set my ground level to be 0. My x initial is 0. Do I know where it ends? No. Do I know its initial speed? And here we can make a reasonable assumption that it started at rest on the ground. So I can make an assumption that that started at 0. Do I know how fast it's going? No. So don't know these, they're blanks. Now what am I looking for? Find out where the rocket is. So which variable tells me that? Well, where is a position? Where is it at a certain amount of time? This is what I'm looking for. This one, just leave it blank, because we don't have information about that. So we want to know where it is at time 1 second, 2 seconds, 3 seconds. Okay, so we filled out our chart. We have our knowns and our unknown. We want to pick an equation that gets us our known. So we have 3 equations, and let's see, we need something with x final in it. So the first one I jumped to is the one that starts with x final. Let's see if that will get us what we need. X final equals x initial. Okay, so this is what I want. X initial, I know that. V initial, I know that. Time, yep, I'm given the time, 1/2. Ta-da! Works. Okay, we don't need to do a second equation. We have this one. And then when I get to this point, I like to cross out my zeros because that makes things less messy. So really the equation I have is pretty simple. 1/2 AT squared. Okay, I know A is 1.5 and I know my time. So now I can get my position at times 1, 2, and 3. It's going to be 1/2 times acceleration times my time. So I'll start with 1, and that's going to be 0.75. And then the other 2 at time 2 seconds, so I put 2 in there, that's going to be 3 meters, and then at 3 seconds, it's going to be 6.75 meters. Okay, answered the first question. This gives me meters per second squared times second squared ends up with meters. Is that reasonable? Okay, so 1 second, it's only about 3/4 of a meter off the ground. Yeah, it's about waist high. At 2 seconds, it's 3 meters off the ground. Okay, so about 10 feet, yeah. 3 seconds, it's accelerating, so it should be getting faster as it goes up, getting more distance. Yep, seems reasonable. Okay, so we've checked our answer. Now part B was how fast is the rocket going at 3 seconds? Here's where we're going to solve for V final. So what is V final? How fast is it going at 3 seconds? Again, I need an equation that's got V final in it. I have V final squared equals V initial squared plus 2A delta X. I have V final equals V initial plus AT. Okay, so which one of these is going to work? I want V final, I know V initial, I know 2, I know A, and now delta X is X final minus X initial. Might look like we don't have that, but we actually know X final at 3 seconds, so I do have that. Looking for this, I know that, I know that, I know that. That one looks easier, so both of these will work. They'll give me the same answer, but this one looks easier, so I'm going to choose this one. Now V initial is 0, so V final is AT, which is 1.5 meters per second squared times time, which is 3 seconds. So the answer to that should be 4.5. Yep, 4.5 meters per second. And that's a reasonable number. That's about 9-10 miles an hour. So after 3 seconds of thrust, model rocket, or real rocket, doesn't say, going about 10 miles an hour, sure. Okay, so have we answered the question? Find out where it is at 1 second, 2 seconds, 3 seconds. That, and that. How fast is it going at 3 seconds? Yeah, we've answered the question. All right, so that's the first part. And now, second part. It says the rocket's engine is burned out at 3 seconds, so it only had 3 seconds worth of rocket fuel. And it starts to move under the influence of gravity only. How high does the rocket go? All right, so now we have a new process that we have to follow. I think I can use the same picture, just we're starting with the rocket up here now, and it's no longer thrusting, but it does have some initial velocity. And we want to know how high it goes. All right, so what do we have? We have a new chart, new set of knowns and unknowns. It's burned out at 3 seconds and it starts to move under the influence of gravity only. How high does the rocket go? All right, do we know where it is at 3 seconds? Yes, we do. It is at 6.75. Do we know where it ends? Well, that's what we're looking for. Do we know how fast it's going when the rocket thrusters fail? Yes, 4.5. All right. Do we know how fast it's going? What's the question? How high does it go? Now, you do know how fast it's going. When it reaches its maximum height, what is its velocity? You got it? You got it? Hopefully you're right. Velocity is 0. So the velocity is 0 at its maximum height, so we have that information. Do we know its acceleration? Well, it's no longer 1.5. That was the rocket acceleration. The problem says it starts to move under the influence of gravity only. We do know the acceleration. The acceleration due to gravity is 9.8 meters per second squared, downward, negative. Do we know anything about time? Nope, so we just leave that blank. All right, so we have our knowns, we have our unknowns. I'm still using the same coordinate system and picture, more or less. We need to find an equation that'll give me what I want. Okay, so I want to know x final. Well, look at that. There's my x final equation right there. Is this going to work for me? I want to know x final. I know x initial. I know V initial, don't know time. I know A, don't know time. Shoot, that one probably isn't going to work. Okay. Do I have another equation with x final? Well, the second equation I usually use is this one. That doesn't have x in it at all. How about this one? I only have these three to work with. Let's hope this one gets us something. V final, I know. V initial, 2a, right there. Remember that delta x, the change in position, is x final minus x initial. There's my x final hiding. So I could use this equation, I'm pretty sure, because I know V final, I know V initial, I know 2, I know the acceleration. I could find out what the change in position is, and then if it started at 6.75 and I know the change in position, I could figure out what its final position is. All right. Is anything 0? That one is 0. Okay. So 0 equals V initial squared plus 2a delta x, and I'm looking for delta x. So if I rearrange it to solve for delta x, I get a negative V initial squared over 2a. That negative makes me worry a little bit, but let's just keep moving on. So negative V initial squared, so 4.5 squared over 2 times the acceleration, negative 9.8. Oh, don't have to worry. Negative and negative, they cancel out. So if you do the math, you get delta x is 1.03 meters. All right, so this is the change in the position. So it started at 6.75 and it went up another 1.03 meters. So its final position is 6.75 plus 1.03 is 7.78. Yeah, so I can round that to 7.8 meters. All right. Did I answer the question? How high does it go? Yes. It reaches a maximum height of 7.8 meters. Is the unit reasonable? Yeah. Is the answer reasonable? 8 meters. Okay, so it had reached 6.75 meters with the rockets thrusting it upward, and now it's coming to a stop due to gravity. So yeah, I wouldn't expect it to go very much farther. So I think that's reasonable. Okay, so there's number 2. Number 3, if the rocket is at its peak height, if the rocket is at its peak at the height you calculated, there, how long does it take to reach the ground again? Okay, so my answer, let me just write down 7.8. Okay, what do we have? So now the rocket went all the way up there, and now it's falling back to Earth again. So it was at 7.8 meters, now it's falling back to Earth. We want to know what our time is. Okay, so how much time? How long does it take to reach the ground again? And that's a poorly phrased question. I'm sorry about that. I try to avoid the phrase how long for questions because long could mean, how long could mean distance or it could mean time. So sorry about that. I'll try to be better about phrasing things like that because how long, particularly for a native English speaker, how long usually means time. We usually interpret it as time. But how long also can mean distance. So I will be more careful about that. All right, what do we know? What do we know here? The rocket is at its peak at the height you calculated. How long does it take to reach the ground again? Well, okay, how long? In this case, time. It starts out at its peak height. Where does it end? How long does it take to reach the ground again? Ends at 0. V initial. How fast is it moving at its peak height? Well, from part 2, we know that at its peak height, it's not moving. Do we know how fast it's going right before it hits the ground? Nope, we do not know that. Do we know its acceleration? Yep, because it's falling under the influence of gravity, so negative 9.8 meters per second squared. Okay, so we're looking for time. And now sometimes it's easiest to look for the thing you want. In this case, find an equation with time. Sometimes I like to look at what we don't have. There are 2 of the 3 equations that have V final. We don't know V final. So I'm going to see if I can solve this with the one equation that doesn't have V final. So I'm going to start there. All right. There's my equation. Do I know x final? Yes. Do I know x initial? Yes. V initial? Yes. I'm looking for time. I know 1/2. I know my acceleration. I'm looking for time. And you look at that and you say, man, it looks like it's a quadratic. Yuck, right? So let's cross out the zeros. X final is 0. V initial is 0. So this simplifies down to something that is not a quadratic. Aren't we happy about that? Okay. We are looking for time. Bring that over. Negative x initial equals 1/2 at squared, 2 over equals at squared divided by a, 2x initial over a equals t squared. Square root that puppy, and negative 2x initial over a. All right. I know x initial is 7.8. I know a. Again, I'm nervous because that negative sign. You can't take the square root of a negative sign if we're in the real world. Let's see what the numbers tell us. So negative 2, x initial is 7.8 over a, negative 9.8. Okay, we're good. Negatives cancel. If you do that math, what you end up with is 1.26 seconds. So is it reasonable that it takes 1.26 seconds to fall? Well, it took 3 seconds of thrust to get up, and then it was probably a short amount of time to stop, and then it's falling. It took over 3 seconds to go up, but if you think about it, that was accelerating upwards at 1.5. It's going downwards at 9.8, so almost 10 times as fast. So yeah, it's going to be a lot faster. So I think this is reasonable. The unit matches because we have meters over meters per second squared. So the second squared comes up, meters over meters, so we have the square root of second squared, that's a second. So unit is good, the number is good, we've answered the question, right? How much time does it take to reach the ground again? Yeah. Now, you can solve this a second way. If you don't like quadratics, if that formula is like, it might be a quadratic, then one of the things you can do is you can use this equation, the one without time again, because we don't know time. If you look at this, we know everything but V final. So you can solve this equation for V final, and then V final equals V initial plus AT. Then you can use this equation to solve for time. And you will get 1.26 seconds if you're careful. There's one thing to be careful of with this. V final is going to be the square root of, V initial was 0, right? Yep. Of 2a delta x. When you take the square root, there are 2 possible answers. You have to decide when you get a V final answer if it's going upwards or downwards. In this case, it's about to hit the ground. You better choose that negative. It's moving down. So if you choose the negative root to put into here, you will get the same answer as 1.6. If you choose the positive root, you get something that shouldn't match and shouldn't make sense. So that's something to be careful of. All right, so this is the general process for solving kinematics problems. We draw a picture. We include our coordinate system and our origin. We determine our knowns and unknowns by using this chart of 6 variables. We find an equation that has what we want in it. So that's this way. Sometimes you can solve it by picking a second equation. So here, if I use this equation, I need V final. I can get V final from this equation. So that would be a process where you use the second equation, solve the equations, check your answer, units, reasonableness. Did you answer the question? So that's the general process. So we're going to be doing this for probably 2 weeks. We'll be doing it with simple kinematics. These are fairly simple. We'll be doing it with more complex, like multi-stage kinematics problems. And then we're going to move on to 2-object problems. So where we have 2 objects and we want to find out like where they meet up. And then we move into 2-dimensional kinematics, so projectile motion, where we're going in the x and the y direction. So we're going to be using this process for several weeks, so get used to doing it. And if you want an A in the class, you'd better have something very clear, because in order to get the high passes that we'll talk about next week, you will want to make something very, very clear for me to follow. All right, that's a great job. Thanks for listening.